Yeah. So, so these are the a few experiments which we are discussing about how the web packet dynamics reveal the same observation what was observed on the real-time femtosecond experiment by Professor Ahmed Joel. So that will end. That will be end of this course. Course in a sense is that I want to give some glimpses of the experiments which currently people are doing in a much sophisticated way, but these are the few experiments which you wonder if you look at it, you will get some idea how the femtosecond chemistry reveals the photofragmentation and also trapping of the transition states. Right? So that is the idea of this. Okay, so this is, I think, one of the example like methyl iodide, which gets photofragmented. This signal is, if you look at this, is the after photodissociation of methyl iodide. This is the iodide signal. Now, iodide is basically trapped using the multi-photon ionization. Right? So now what we see is that initially the intensity of this ionization of iodine, which is formed after photofragmentation of methyl iodide, is going to be very low, right? And then it reaches to a maximum and it becomes a plateau, right? So what it reveals basically is that it takes almost 0.4 picosecond. So this is a picosecond time scale, and the intensity starts somewhere here. So that is approximately 0.4 picosecond times required for the dissociation of methyl ions. Right? So this can be explained using the potential energy curves. Like if you look at for this, so this is something like this is again this is two-dimensional curve, right? So we can have the idea of excited state potential energy surface of methyl iodide using the emission process also. So that part I am not going to discuss. I just thought that is not that important, but we can map the excited state potential energy surface after excitation, and then if it is going to come back to the ground state, so that emission intensity from the emission intensity, the potential energy, emission energy, you can get the potential energy of the excited state, right? So I'm not going to do that, but what we are going to do it here is that to find out what is going to be the time taken for this methyl iodide to be fragmented completely. Right, okay, so this is again a palm probe experiment. The methyl iodide, this is the ground state, and then we are taking the molecule, ground state molecule, to the excited state using the pump laser. It goes to the excited state. Now, excited state again, it's a dissociative. This dissociative state, now when it goes to the excited state, it's slowly start separating, like methyl fragment and the iodine fragment. Okay? Now, we what we do is that we apply the probe pulse. That is another pulse which identify the ionization of iodine, right? I to I plus. Methyl group remains radical remains as it is. Right? Now here actually it is used multi-photon ionization. This technique is called multi-photon ionization. Here we need 3 photons to ionize the I to I plus. Right? So we can separate this I plus using the different electric field. Like if we take pass through this electric field, so that means the plus charge will be reflected towards the electric negative pole of the electric field. So that is the way we identify the I plus. If you want to, it's like how the ion moves to an electric field. Okay, so if we do this, so that means the idea of this is that, like, we apply the pump, then with the time delay, now here it is in picosecond, we apply the probe pulse. Now here the probe pulse is set in such a way that iodine is getting ionized with a 3-photon ionization, right? So if we do that and slowly we vary the time delay, what we realize that, like, in this, until this almost 0.4 picosecond, there is no intensity, right? So after that, slowly this increases, because when it is 0.4 picosecond, it's almost dissociative, and then if this resonance condition is set for the ionization of iodine to the I plus. Okay. So that's what the intensity is getting flattened, because when it comes here now, is all the iodine is going to be in the resonance condition, so it's going to go to the I plus. And it was found that this maximum limit, I mean the upper limit, is that it takes 0.4 picosecond to do the separation of the methyl group and iodine. Okay, so this is a very simple experiment to find out how much time it takes for the methyl iodide to get dissociated. The second part of this, which I am not going to discuss right now, but just to let you know that if it is like we do in a if we allow this methyl iodide to fluoresce back, let's say to this ground state, then from this energy difference we can plot the excited state potential energy surface of this, and that reveals one thing you can realize, that this when during the dissociation of methyl iodide, this methyl group is going to perform the kind of umbrella motion of ammonia, because this is going to be with a radical. So therefore we have a like, along with the separation of the methyl and iodide, this flattening of this methyl group is also going to take place. So that reveals the how the excited state potential energy surface is going to be looking like. Okay, so this is kind of like experimental observation of the photofragmentation for the methyl iodide, and this of course gives you idea what is going to be the upper limit of the photofragmentation of this. Let's go to that. Okay, so the next experiment is the photodissociation of alkali halide molecule. Now here it is like this is just a reaction. What I am going to say is like M is the metal, X is the halide, so it can be sodium iodide, like that. Right? Now here what we'll basically try to trap is that this is first this alkali halide molecule is excited to the excited state. Initially it was ground state, then you apply the pump pleasure, go to the excited state, so that is this, and then when it slowly gets separated, this is kind of fragment. It's not completely fragmented, but this is kind of a transition state type structure. So it is bonds getting elongated, and then finally it is going to be completely broken. So what we'll try to do, we'll try to do this trapping of the identification of this transition states, and also when it is getting complete fragmented, right? Like if I take sodium iodide, then initially sodium iodide will be in the ground state. With the pump laser, we are going to take it to the sodium iodide excited state, and then okay, you have to realize the ground state sodium iodide is going to be ionic curve. I'll just discuss it, and excited state will be covalent. So that is excited state. Now when sodium and iodide is getting separated, but not completely separated, so that is kind of transition state. We are going to get signal if we probe this. This is called transient species, and then after certain time is going to get dissociated. Then we can probe the metal also, sodium, right? So we can have two types of signal, and we can see what is going to replace, right? Now here is the experimental observation of what I am going to show you. Now look at here, when it is like look at this signal is the upper signal. If you look at here, this is free fragment of sodium, right? And the bottom one, which is solid curve, is basically identification of sodium iodide. This species, right? It's not fragmented, but this is a kind of transient species. Right? Now, if you look at here for the transient species, if you are probing this transient species, look at this initial signal is quite high, highly intense. Then it is intensity is reducing and kind of behaving oscillatory behavior, right? And after certain time, let's say here it is showing 3 picosecond, it is fragmented kind of thing like sodium plus iodine minus. So it's not completely fragmented because it's an activated complex, but there is a separation, right? Now initial structure, this one 0 time delay, it is showing that this is basically intensity of the sodium iodide when it is excited, right? So this is excited sodium iodide without separation, so that time is taken to be 0. The intensity is maximum. Now is with time delay, it's a oscillatory curve of this sodium plus iodide minus. So this is the structure kind of like sodium here, and this is iodide here, right? Transition state, and that is oscillatory behavior it is taking place. Now if I trap the only sodium when it's completely separated, then initially this is going to be the sodium. Then look at here again, after certain time this intensity of sodium increases, and that time period, look at here, it is matching with the second peak of the activated complex. Again, if you are going the oscillatory one, that is like a stair like structure, that is kind of this oscillation, this stair is matching with this one, the third one signal. It's like that. So that means this signal matches with this one. So that is 0 time. This is for the second one. This is third one. So that means two oscillations are matching with this. Right? Now, how do we really explain this? So what here the experiment, what they have used two pulses, of course. One is pump one, that is not shown here. The probe ones is that like two, one is the lambda 2 infinity stands for the final products. This is here in this case sodium, trapping the sodium, and if it is a little bit red shifted lambda, so that is lambda 2 taking the transition state. Transition state means this one, M dot X, this one tapping this. So two signal you are getting. This one is going to be for the transition or activated complex, this oscillation. Look at here, intensity is decaying. Now in this case, this is sodium. This intensity of the sodium is accumulated. So there are two different observations. So let's see how we can explain this. Okay. Here is the potential energy curve, left hand side. Look at here. This is, if you recall, the we have discussed is a harpoon mechanism with the sodium and bromine molecule. Here it is exactly similar type of curve, but this is for sodium and iodine. So I go from this side to this is like a product. So this is going to be just a minute. I can hold it for some time. Start it. Yeah. So coming back to this, so this is like as I said, this is kind of harpoon mechanism what we discussed before, and that is kind of, this is the covalent curve. If you look at here, this is sodium plus iodine, that is infinitely separated. Now slowly when they are coming closer, then it's a covalent curve. Energy is kind of going to be flat. Now when it comes very close, then the repulsion start taking place, right? So I'm still covalent curve, and curve is going to go like that. Okay. So this is the covalent curve. I'm drawing this curve, let's say on this covalent curve. This is no repulsion, is flattened. Then when it is coming closer, then it start getting repel, and this energy is going to go up. Okay, so that is the covalent curve. Now when it comes closer, now ionization potential of sodium, so that means outer shell electron is very low, and electron affinity of the iodine is quite high. When it comes closer, there is a point, this covalent character is going to change it to the ionic curve. Let's say that's a different color. If I take that is blue, right? So then at this point, what happens? It's kind of harpoon mechanism sets up. Like sodium throws its electrons as a harpoon, and iodine it picks up, and then it gets ionized, and then because of the Coulombic interaction at this point, the ionic character sets in, and it follows this kind of curve, right? Of course, like if it is coming from infinite separated, that curve will merge with the sodium plus and iodine minus. So that is basically, this is the energy difference between the energy required for the ionization of sodium and electron affinity of this iodine, right? So that is the energy difference, delta E. So that's what we discussed for the harpoon mechanism. Okay, now this is actually curves. This is the covalent curve. This is the ionic curve. Now this part is going to be the avoided crossing, right? So it is kind of let me take another color so that we, okay. So when it comes here, so there will be a avoided crossing. So it is going to be like that, and this curve is going to be like that. Okay, so that means, and of course the resultant curve is going to finally it's going to go like this, because the time repulsion is going to go there. So I'm not going to discuss that, but what we found is that the excited state, look at here, is kind of well like this, right? So this was covalent, then when distance increases, now it is merges with the ionic curve, right? And this one, the ground state one, is this is the ionic curve, goes like this, then it becomes converted to covalent curve. Okay, so the experiment is done like this. Initially, the ground state sodium iodide is taken with the pump to this. So this is the wave packet, this one. Then this sodium and iodide bond distances increases, so going to get separated, and we apply the probe pulse to trap this in this region. So let's say I'm giving in this to take the, so that is the lambda 2. So this is lambda 1. So that is the pump one, and this is lambda 2. Now delay time is let's say whatever the time it takes up to this. Right. Now I can have my probe pulse, which can be with the resonant condition with this sodium. So if I can take sodium to the excited state, right? So that is written as lambda to infinity. So that means it is completely separated. This is sodium in the excited state. Sodium star. Okay, so if I do this, then what we get? So this is lambda 2. This is also lambda 2, but the two different lambda, the probe pulse is like that. This is when sodium is infinitely separated, and this sodium is getting excited to the sodium, excited sodium star. But in this case, this is detuned. So that means in this case, lambda is set in such a way that this is taking this sodium and iodide in the transient species, it is taking to the excited state. Right? So that is the difference. So so those two curves, what you get here actually, this so far this one is the transient one. So this trapping, this one, if you can look at here, so that is getting oscillatory, but again intensity is getting reduced. That is, so that is activated complex. Now this one is the excitation of the sodium. So that means when it is completely fragmented, sodium to sodium star, and this intensity is getting accumulated with, of course, oscillation with at the same interval of this. Right. So that's what we are trying to explain. Okay. So now if I go there, how we can explain this? Experimentally, it was difficult, of course, to find out. So therefore, the theoretical people, they came up with the wave packet propagation, and what they did is basically like this. They have excited the wave packet, now allow this to evolve, and this is with the time scale. You can look at here, this is the wave packet picture. Now from when it is here, the overlap integral you can think about with this initial wave packet and the time evolve packet, overlap integral will be maxima. Now when it is moves here slowly, it's the time delay, you can look at a 200 femtosecond, this is 160 femtosecond. Then it becomes splitted into two parts. This is dark one, and this is lighter. Right. Again, if we move the wave packet further, what you will realize is that out of these two parts, one is going to go in this direction, that will go in this part, and the other part is going to come back in this direction. So that means going to go back. So look at here, this part is out of this well, and this part is going to go back. So that means the wave packet is going to move here. When it comes here, there is a chance of tunneling. This is the upper surface, the lower surface. There is a chance of tunneling. So some part of the sodium iodide tunnels through and go to the covalent curve, but rest of them is going to go back. Right. Again, it comes here. Again, it happens the same thing. So when first time sodium is going to come here and we trap this sodium, the intensity of sodium is going to be less. Right. And then when it comes again back, so I'm having earlier sodium plus second time it's coming sodium. So total intensity is going to increase, but with a step. Now, if we look at the other part, what happens? So that means the transient species like this in this region. Initially, the transient, the activated complex intensity would be high because that is not decayed. Then when first time it goes here, some portion has already moved to this. So now second time when I trap this transient species, the intensity is going to be low, right? So like this will be oscillatory. So each time wave packet comes here, some portion goes to tunnel through this and some portion goes back. So I'm going to get oscillation. So when it goes this with the sodium, I get accumulating intensity, but when I trap the transient species, the intensity is going to get reduced. So that's what the intensity we get here. So this is the sodium curve. So every time sodium leakage through this upper curve, I'm going to get accumulated oscillation. But this is activated complex. So every time it leaks, the intensity of the activated complex get reduced. Right. So that is the way we can explain this, and that's what both the theory and experiment was complementary each other, right? And finally, you will see that this is the time delay wave packet, how it goes. So first 160 femtosecond, it just moving in this direction. Then slowly it gets splitted. Splitted in a sense is like when wave packet comes here, it fills the boundary, and some portion goes like this by tunneling. So that's low, smaller portion goes to tunneling, and this is going to come back. So that's what when you again time delay, then you will realize that this part is going to come back and this is going to go ahead. And this is repeating for a couple of times unless it is going to be broken completely. The reaction is going to be completed. Okay. So this experimental observation was not able to explain how this is possible unless until we do the theoretical work, or we generated the potential energy surfaces, the covalent and ionic curve, and to do the wave packet dynamics. Okay. So this wave packet dynamics reveals that these oscillations both in the sodium signal and in the transient species is going to be there because of the tunneling through this oil, upper state oil of the wave packet through this in a sequential manner. Right. So therefore, we are going to get oscillations in the experimental curve. So this is for the activated complex with the reduced intensities, because every time it leakages through, the activated complex intensity is going to get reduced. But every time it leakages through the well, my sodium intensity is going to be increasing. Right. but the oscillation will be at the same place because it's the same place the wave packet is going to be broken. So that's what is the signature. We explain this, right? Again, there are two pulse were used to probe these intensities. Okay, so that is kind of, it indicates this experiment. Therefore, it indicates that in this case, the sodium iodide was trapped in this potential well for a certain period of time, and finally it completely decays, right? So that is kind of, it says that after femtosecond chemistry is the photofragment trapping in alkali halide photodissociation, right? So this is kind of very interesting experiment. What it really reveals that we can use the palm probe experiment to trap the transient species, and it was shown by Professor Ahmed Joel in late 90s, right? And still some people are doing this kind of experiments, and it's very fantastic. Of course, very sophisticated instrument has come up now. So, so that's what the experiment. If some of you get chance, I think you will be able to, I think, do it. So with that, I think this is, I'm going to stop